I welcome you all in this presentation related with the subject materials processing, fundamentals and practical. And we are talking about the metal casting. And in this particular presentation, I will be focusing on the different ways by which the performance of the casting can be enhanced. The performance means the mechanical properties which determine the load carrying capacity and the life of the castings under the given service conditions against the external loads. Okay. So, as far as the content is concerned of the presentation, this will include like enhancing the performance of casting. So, in any case, whatever the casting has been made, if it is sound, means if it is free from defects, then at least as per the kind of the metal which is there, its load carrying capacity, it will offer the desired characteristics for a given grain or the phase structure. Okay. But if the casting is not sound, then what will happen? In presence of the defects, the performance is compromised very badly. Why? Because you see, these defects reduce the load resisting cross sectional area. So, actual amount of the area which is available, that is resisting the external load, that is reduced, and therefore load carrying capacity of the casting is reduced depending upon the kind of stresses which are being applied, maybe like say the tensile, shear or the compressive. If due to the defects, if load resisting cross sectional area is reduced, then certainly the mechanical performance of the casting is going to be compromised very badly. Not just that, presence of the defect like porosity, inclusions or the cracks, these also act as a stress raisers. So, stress raisers, okay. So, these stress raisers means stress will get localized, means the stress concentration will be very high. Say if there is a casting, okay, of a particular section and this is having a kind of stress raiser like this. When it is subjected to the external load, the stresses at other locations where there is no defect, the stresses will be nominal, okay, but the stresses will tend to get localized wherever there is a defect. So, there the maximum stress will be determined by the size of the defect and the tip radius of the defect, or the crack which is there. So, greater the defect size or smaller the radius of the crack, these will be increasing the stress concentration, means these will be increasing the maximum stress that will be encountered at that particular location, and that in turn even for the lesser load it will be causing the higher stresses, and therefore the load carrying capacity is compromised very badly. Therefore, it is very important that casting whatever is produced, that is sound, it is free from the defect. And what we can do to do that, like say develop the suitable casting procedure. Okay, what the procedure means, all the steps which are being used for development of casting will be the part of the casting procedure, whether it is making pattern, okay, molding, melting practices, melting of the metal, then melt treatment, then pouring of the molten metal and followed by the solidification, the role of the riser, while it is taken out, the casting should not be get damaged. Okay. So, all the steps which are related, say once the casting has been solidified and it has been cooled down to the room temperature, the post casting treatments, okay, which may be in form of post casting heat treatment or any other kind of the treatment which is to be done for realizing the desired microstructure and mechanical properties. So, it is very important that the casting procedure is established properly. Okay. So, the developing the suitable casting procedure is one part, and say despite of this, if the defects are there or in the casting, then we need to take the corrective measures. What it includes? Corrective measures like, let us eliminate or reduce or eliminate the defects from the casting if it has been made. Okay. So, for that the methods like maybe short peening, the surface layer defects will get closed, the remelting using the laser or the TIG, that will help to eliminate the defects like porosity and inclusions and cracks, and controlled surface layer deformation like the burnishing, friction stir processing, or the rolling of the surfaces will tend to close these defects or will break these defects for elimination of these defects and consolidating the surfaces. So, few corrective measures can be taken to enhance the soundness if there are defects. Sometimes the design of the casting is not proper, okay, and if that is there, like it is causing the sharp change in cross section. Okay, sharp change in cross section means there it will increase the tendency of the stress concentration, it will increase the tendency of cracking due to the stress localization, and which in turn will reduce the performance of the casting. So the stress results must be reduced, so that it is the casting is designed in such a way that there are the fewer stress results or no stress results, or say that can be done by designing the casting in such a way that it avoids the sharp transition, sharp change in cross section, or if it is there, say due to the requirement of the casting procedure, then we need to either make the suitable fillets by the machining. Okay, let us do the machining of those all sharp corners wherever the stresses can localize to encourage the initiate the cracks and cause the failure. Okay, so the fillets, machining, or avoiding the sharp transition, these can be looked into to see that unnecessary stress concentration from the casting itself can be minimized. Another way of improving the casting performance is to make the inherent changes in the metal itself. Okay, say this is the casting and it is sound. It will be offering certain set of the mechanical properties in as cast condition. Okay, so if you want to enhance the say yield strength, ultimate strength, or the percentage elongation or the toughness, to enhance this, it will be important that the microstructure of the metal of the casting is modified. Okay, so like say the grain refinement of the casting, this is one, or modification of the certain constituents which are leading to the degradation in the or resulting in the lower properties. Say if it is having the needle shape structures, then needle structure is to be modified. If the grain structure is very coarse, then this needs to be refined. So depending upon the kind of metal systems we are dealing with, we need to design the suitable treatment for realizing the desired microstructures so that the performance can be enhanced. So this can be done even during the casting. You see, we can do the grain refinement, okay, or we can do the modification by suitable alloying, or after the casting, once the casting has been made, then what we can do is the post casting heat treatment. Okay, this post casting heat treatment will allow us not just to change the size and shape of grains, but also it will allow us to realize the desired phases. It is possible that the casting in as cast the casting or the product which has been made in as cast condition is having certain phases. Say it is having the phase alpha. If this is not offering the desired set of the properties or one which is expected, then this can be modified by controlling the microstructure through the heat treatment, so that not just the size and shape of the grains is modified, but also the kind of phases or the kind of the compounds, say IMCs, which are there, that is produced in order to enhance the characteristics of the castings. So depending upon the kind of metal, say if the metal composition is such that the casting composition is such that it allows the precipitation hardening, then we have to do the suitable T6 or T4 heat treatment, so that the fine precipitates in the casting can be made for enhancing the performance of casting. But if it is like the transformation hardenable kind of systems like steel or cast iron, then what we need to do is, let us go for the suitability heat treatment, like through the austenitizing followed by the controlled cooling. Okay, this controlled cooling will allow us to do the annealing if you want to do the softening, or if you want a strengthening, then normalizing, and if you want a strengthening coupled with a good combination of the toughness, then quenching and the tempering treatment. So, the kind of the heat treatment we need to do, that will depend upon the purpose and the target properties which are desired. Even sometimes the heat treatment of the casting is done primarily for stress relieving. Okay. So, because in the casting, if there are residual stresses, okay, residual stresses, the casting during the machining will tend to distort the shape of casting. That is one. Or later on also it will be reducing the mechanical performance of the casting. It will be reducing the fatigue resistance of the casting. So, the dimensional stability of the casting is compromised in presence of the residual stresses. So, if we do the heat treatment for doing the for stress relieving, then residual stresses will be relieved, and the tendency of any kind of the distortion during the post machining of the casting will be avoided. Even the mechanical performance is enhanced. Okay. So, it is important that the as means this is a casting heat treatment of the casting is one of the ways to improve the properties and performance of the casting. Okay. So, as I said, the soundness of the casting means making all the procedures of the casting in such a way that the made casting, whatever is casting is prepared, that is free from defects. Okay. So, casting procedure including the designing or making the pattern such that it avoids any kind of the stress concentration or the stress ratios, molding practices in such a way that it avoids any kind of the defects like the misrun or any other kind of porosity inclusions, whatever the kind of the defects which can arise due to the improper the molding practices, then that should be taken, means that should be established properly so that the related defects are minimized. Melting should be done in controlled environment so that the unnecessary entry of the gases in the molten metal is minimized, and then the molten metal is given desired treatment in form of degassing, fluxing and treatment, so that we supply the clean molten metal with the at the desired temperature to the mold, so that the desired sound casting is realized. If it is not so, then that will certainly increase the tendency of the defect development in the casting. So, pouring, desired proper temperature and the proper filtration of the molten metal, so that the the molten metal at correct temperature and in pure form, free from the impurities, is supplied, and that too very smoothly, to avoid any kind of the turbulence which can damage to the mold and create the defect in the casting, or it can increase also excessive unnecessary turbulence can increase the pickup of the gases and entry of the gases into the molten metal, and later on in the casting that will be promoting the defect in the casting. So, pouring has to be done in such a way that there is a proper temperature, proper filtration to remove the impurities, and the feeding of the molten metal to the mold is smooth. Withdrawal of casting, it should be done at right temperature to avoid any kind of the damage to the casting, because if the casting is withdrawn from the mold at a higher temperature, then this can damage to the casting and increase the defects on the casting surfaces. And it also has to be established properly that what kind of the defects will be accepted during the inspection and testing. So, suitable acceptance criteria need to be established, otherwise what will happen, if any inconsistency will lead to the release of the castings with the defects which may not be acceptable. Okay. Then the corrective measures, if there are defects in the casting, then this we need to, either we can just simply discard the casting or we try to repair the casting. So, the defective casting, we need to take this corrective measures to reduce the defects, especially the surface defects, or if there is internal defect which cannot be corrected, then casting will be discarded. Okay. So, one of the simplest method is, like say there is a defect in the casting like this, okay, inclusions, this casting surface. So, this is inclusion, these are the, like say, the open holes and the cracks like this. So, what we need to do, we have to gauge. The one approach is we just remove this section, that is called using suitable flame or arc, this metal this section is removed. Okay. And wherever there is a defect, that section is removed, then it is filled in using the suitable low heat input welding procedure. Okay, so we just fill that section wherever from the metal has been gouged out, and the defective section has been removed, and that will be filled in using the suitable low heat input welding procedure. So maybe we can use the SMAW or TIG welding also can be used in order to eliminate the defect and do the by repair welding, eliminate the defect to have the sound casting. If we have the situation like this where there are the defects at the surface like this, so what we can do, you can use the suitable heat source which may be in form of the laser beam or arc. So, the laser beam or arc, these will be supplying TIG arc, these will be supplying just the heat at a relatively higher power density than the flame. So, what it will be doing, it will be melting the surfaces up to certain depth, okay. Then the arc is moved over the surface, and this arc or the laser beam will be causing the melting followed by the rapid solidification. So, what it will be doing, initially the molten metal will be created. If there are defects, they will be closed. If there are inclusions, they will be floating and will be coming at the surface, followed by rapid cooling. Okay. So, what will be happening, initially the casting may be of very coarse grains, but when the rapid cooling is applied or experienced due to the melting of thin layer at the surface, rapid cooling causes the significant refinement of the grains. Okay. So, the casting, bulk casting may be of the coarser grains, but the surface layers which has been melted, remelted by the TIG arc or by the laser, it will be resulting in the very fine grain structure which is sound after the solidification. So, the TIG remelting allows us to develop the sound casting with much better characteristics and mechanical properties due to the grain refinement. Okay. Then there are other methods of corrective measures like the cracks and inclusions like this. So, what will be done, like these are the methods: short peening, friction ester processing, burnishing, and the rolling, normal rolling or contour rolling. Okay. So, in all these methods, what is done, the controlled surface layer deformation is realized. This deformation is plastic in nature. So, plastic deformation is realized. So, for short peening, you see the steel balls of say 2 to 3 mm are accelerated at a high speed. They are directed onto the surface of the metal. So, it will be causing the localized surface deformation like this, and this in turn will be causing the closure of the porosity and fracturing of the inclusions and closing also of the cracks, especially in ductile metals. So, when this kind of the short peening is done all along the surface, these benefits will be realized because of the controlled surface deformation which is realized by directing the high velocity steel balls onto the surface of the metal, which is really a little bit ductile also. So, what it will be doing, causing the controlled surface layer deformation, that in turn will be closing the porosity, closing the cracks and breaking the inclusions. So, this kind of the modification will be resulting in the two benefits. One is work hardening and second is the elimination, okay, or removal of the defects. Okay. And when the work hardening coupled with the removal of the defects, that is realized, also the surface, this kind of the control surface layer deformation will be causing the refinement of the grains at the surface. So, all these benefits, whether it is a friction ester processing, burnishing or the contour rolling, all these will be helping in realizing the work hardening coupled with the closure of the defects, okay, or reduction of the defects, okay, and sometimes even the refinement, especially in the burnishing and the friction ester processing and short peening. All these will be causing the work hardening, grain refinement coupled with the closure of the defects. Okay. So, as far as the approach is concerned, in burnishing we use the roller like this and it is pressed against the surface, say having the defect. So, the roller is like this and this will be pressed against the roller. Roller will be passed over the surface, and so this will be causing the controlled surface layer deformation. In case of the friction ester processing, say that it is having the defects. So, what we do, we use one tool, this is shoulder, and the shoulder with the pen like this, and it is rotated. So, the pin will be causing the controlled surface layer deformation of the near surface layers, and a significant deformation of the metal at the top surface will also be occurring when it is traversed across the surface. Okay. So, this will also be causing significant, will be producing the significantly fine grains, closing the defects, okay, closing the defects, and also it will be causing the work hardening depending upon the kind of metal. So, the friction stir processing, short peening and burnishing, all these will be doing the similar kind of defects. Similarly, the rolling, like if there are defects at the surface, okay, like this. So, what we do through the rolls rotating in opposite direction, the cast component is passed, and when it is passed, the surface, the deformation, the thickness will be reduced, and that will be causing the bulk deformation of the metal, that in turn will be closing the defects, as well as it will be causing the work hardening. So, all these controlled surface layer deformation related approaches, what they will be doing, they will be causing improving the performance due to the increased hardness and yield strength due to the plastic deformation, and that will be resulting in the work hardening. And the second is the grain refinement due to the excessive grain refinement that will be happening in case of the short peening, friction stir processing and burnishing, and then closure of the defects. So, all these factors in combination will be improving the mechanical performance of the casting, which is defective. So, there are two approaches of correcting the defects. One, three approaches where gouging followed by the repair welding, remelting using the TIG arc or the laser, is also called a TIG dressing, or control surface deformation using the suitable approach. To enhance the casting quality, you see, as I have said, we can adjust the microstructure of the casting. So, there are two aspects related to the microstructural control. One, we can do the grain structure modification, another is the phase structure modification. So, in the phase structure, we try to change the type of phase, okay, relative amount of phases, okay, and their distribution. So, these are the three aspects: the type of the phases, relative amount of the phases, and the distribution of phases, where which phase is present. In the grain structure, we will try to see the size, shape and distribution of the grains. Okay. So, basically for improving the performance of casting, the one approach where the grain structure is modified. So, this can be done by suitable approaches to control the grain structure, where the refinement or the morphology is modified. Another approach where the phase structure is modified, that is done especially in case of the heat treatment. So, during the heat treatment, we try to alter the kind of phases which will be formed, or by controlled alloying we can also develop the suitable kind of the compounds and phases in order to realize the desired microstructure and mechanical properties. Okay. So, the grain refinement, what it does, this is the part related with the grain structure, where the coarse grains of very large size refined. Coarse grains are converted into the fine grain through the grain refinement. Okay. So, what are the approaches we have? You see, there are certain approaches which involve, like this is the molten metal. Okay. So, if initially there will be normal nucleation and the growth mechanism that will be done. So, if there are few nucleants in the beginning, these nucleants will be growing eventually and will be resulting in the coarse grain structure. Okay. So, this is the case when number of nucleants in the casting are few, when we have not done anything, and those nucleants will be growing eventually. So, this will be resulting in the fewer grains which are coarse. What we can do is we can add the inoculants. We can, to facilitate the heterogeneous nucleation, we can add the certain constituents which will act as a nucleating agent. So, in the molten metal, what we do, we try to add the certain alloying elements. Okay. These provides the desired nucleants. These nucleants will be increasing the number of nucleants available. This alloying will be generating lot of nucleants in the molten metal, and each will be growing later on during the growth stage, and that in turn will be resulting in the fine grain structure. So, inoculation, what we do, this is one approach of the heterogeneous nucleation where the nucleants are added from outside. In ferrous metal, we add vanadium, titanium, niobium, zirconium, apart from copper and aluminum. Those are also used as a refiners in the case of ferrous metal casting. In case of aluminum alloys, we use the AlTi-Ti and AlTiB boron and TiB2. These are the common refiners for the aluminum. When these inoculants are added in the molten metal, they generate lot of nucleants, and these nucleants when grow at the growth stage, they will be resulting in the fine grain structure. This is one approach. Okay. The second approach is what? Where the external force is used. External force means we can apply the vibrations to the molten metal. Say this is the molten metal mold, okay, molten metal in the mold. So, if we provide the external force in the molten metal, like say in form of the vibrations, okay, this is one approach where the mold is subjected to the vibrations. So, vibrations what will be doing? They will be having the cavitation effect, that is one. It will be causing a lot of disturbance or turbulence inside the molten metal. So, what it will be causing, like the dendrites which are growing inside the molten metal, because of this turbulence and the cavitation effect, they will be breaking. So, the dendrites, like say this is the primary dendrite, these are the secondary dendrites, and because of the turbulence and the disturbance in the molten metal being introduced through the vibrations, these the dendritic arms will be breaking due to the turbulence in the molten metal. And when these dendritic arms break, each arm will act as a nucleant. Whatever the fragments of the dendrites are created due to the vibrations, they start acting as a nucleant because they are of the same composition, same crystal structure. So, the fracture of the dendritic arm facilitates the creation of the large number of the nucleants, and once the dendrites get fragmented, then we will be creating large of nucleants, and that in turn will eventually be facilitating the grain refinement in the casting. The another approach is in the molten metal, like say this is the molten metal and it is cooling down. So, what we do, like say this is the solidus, this is the liquid. Okay. So, this is the composition. So, here this temperature and above everything will be in liquid state, and this temperature above everything will be in the solid state. So, we try to choose a proper temperature in the mushy zone where we have both liquid plus solid. So, in such a way that there is a 40 to 50% of the liquid and say 50 to 60% of the solid. So, in this case what we do, so we at this temperature, see initially the molten metal in the mold will be allowed to cool. As soon as the temperature reaches to this zone where there is a, like say the 50 to 60% of the solid and 40 to 50% of the liquid. So, what we do? We try to do the stirring using the suitable stirrer in the molten metal. So, we try to create again the disturbance. So, when the disturbance is created, the dendrites which were growing in the normal way like this as a dendritic arm, because of this disturbance in the mushy zone, all these dendrites will be fractured and they will be creating the spheroidal shape grains. Okay, non-dendritic spheroidal shape grains, and when this kind of the structure is produced, it offers the reasonably good ductility and the toughness as compared to the simple dendritic structure. So, this is an approach of the stir casting where the molten metal is subjected to the stirring in the mushy zone for causing the fracture of the dendrites which are growing. Okay. So, this is how we can refine. So, the grain structure, we can do the heterogeneous nucleation by adding the alloying element, okay, or we can use the external force, okay, in form of vibrations or stirring in order to break the dendrites which are growing, and they will be providing the nucleants for the grain refinement. Now, when the grain refiners are added, say if we talk about the grain refiners for the aluminum silicon castings, okay, aluminum silicon castings like say ALTI is one of the very commonly used. ALTIB is the another kind of the grain refiner which is used. The effectiveness of these grain refiners reduces in presence of the certain alloying elements, also as a function of time. It is possible like if we have in excess we have time and here we have grain size, okay. Initially if we say in the mold, if we say in the molten metal, if we add the grain refiner and immediately if that molten metal is taken out, then we get the coarse structure. But gradually after some time, it takes some time for the grain refiners to become effective, the grain size will start decreasing and then this grain size will remain, the grain refinement will remain effective. Thereafter again grain is coarsening starts even in the presence of the grain refiner. So, here the grain size, so, so we have to give like say 1 to 2 minutes initially for the grain refiners to be effective to produce the nucleant, so that the grain refinement can take place and that this will remain effective. But after say after 30 minutes or so, again the grain coarsening starts. Say in molten metal we have added the grain refiner, now it is being taken out to produce the casting. Okay. So, the decrease in effectiveness of the grain refiners as a function of time is known as the fading, the effectiveness of the grain refiners. Okay, this is one aspect. The effectiveness of the grain refiners is also compromised very badly in presence of the certain alloying elements like silicon. So, silicon in aluminum silicon alloy adversely affects the effect of or effectiveness of the grain refiner, that is known as silicon poisoning. Okay. Silicon reacts with the refiners, preventing it from doing the desired refinement during the solidification. So, that is why, so the silicon acts as a silicon causes the poisoning for the grain refiner by reducing its effectiveness to refine the grains. Okay, this poisoning in turn causes the coarsening of the grain structure, which will be negatively impacting the mechanical properties. Now, the microstructure, the modification is the another term which is particularly used in case of the aluminum silicon castings. Okay, so in aluminum silicon castings, basically we get the alpha aluminum like this and the silicon needles. Okay, silicon needles like this. These silicon needles, these reduce the yield strength, ultimate strength, and these reduce the ductility, percentage elongation and toughness. So, if these needles are modified, you see, since the silicon being the aluminum is very soft and ductile, on the other hand needle is hard and brittle. Okay. So, when the needle shape silicon is produced in aluminum silicon casting, it adversely affects the mechanical performance of the casting. So, what is done? There are certain ways we can break these silicon needles into the fine fibrous shape, where fine small size castings like this, castings with the small silicon needles are produced. That is possible using the rapid cooling. But when the casting is very large size, then certainly rapid cooling cannot be provided, especially at the center of casting, and that in turn will be resulting in the needle shaped silicons. So, we need to add the modifiers. So, what modifiers does is like the modifier, this is the needle shaped silicon, it will be broken into the small fine fibrous shape. Okay. So, this fine fibrous shape is less harmful and this is better for the mechanical performance of casting as compared to that of the needle shape casting. So, by adding certain alloying elements in the molten metal of aluminum silicon alloys, what we can do, we can modify the needle shaped silicon into the fine fibrous structure, and this is done by adding the strontium, sodium, antimony and calcium. So, we need to optimize the amount of the strontium or the sodium which is to be added for the modification purpose of the silicon needles, okay, to get the fine fibrous form. So that the performance of the casting can be enhanced. So, the modification transfers the needle shaped silicon into the fine fibrous structure in the eutectic aluminum matrix. The effectiveness of the modifier is also compromised in presence of the certain alloying elements, especially magnesium and copper and phosphorus. So, means if modifier is not working effectively, then it will be producing the needle shaped silicon, and that will be happening especially in presence of the elements like magnesium, copper and the phosphorus in cast aluminum silicon alloys. So, there are several factors that decrease the effectiveness of the modifiers. The cooling rate is another one. You see, sometimes the cooling rate itself is one of the methods for developing the modified structures or modification of the silicon. But if the cooling rate is low, then we need lesser the concentration of the modifiers as compared to the case when the higher cooling rate is used. So, now I will summarize this presentation. In this presentation, basically I have talked about the different ways by which the performance of the casting can be enhanced, say what can be done to eliminate the defects from the casting and what are the different approaches which can be used to improve the microstructure of the casting through the grain refinement and through the modification, so that the mechanical performance of the casting can be enhanced.